All right, let's go ahead and finish up on this project 2. We're going to make a data path similar to the Pentium Pro that we just finished discussing. Fetch will be 1 cycle, fetch up to 2 instructions per cycle. We are not doing x86, so you do not have to worry about complex decode. You will use a bimodal branch predictor with 64 entries indexed by the least significant bits of the addresses of 2-bit counters, taken, weakly not taken, and not taken. That will be similar to previous. An initial state of weakly not taken for each entry. If the first instruction is a branch that is predicted taken, send only 1 instruction to the next pipeline. Both instructions are branches, send only 1 instruction to the next pipeline. Okay, great. You should implement a 3-entry fully associated branch target buffer. That's going to store the targets, in which all branches taken or not taken are entered with LRU replacement. LRU is least recently used. Register rename. Convert the architected register specifiers, aka the registers we're using, for each instruction to physical register specifiers using a rename table of 8 entries, because we have 8 registers. Update the register mapping in the rename table for the destination register. Each entry has a valid bit. 0 means the current value is correct. 1 means that some instruction in the ROB is generating the required value. And a rename index in the ROB for the instruction generating the required value. Then in allocate, you place each instruction into the reorder buffer and the correct reservation station if they're available, because the reorder buffer will have 16 entries. 3 entry reservation station must exist for the add, NAND, and BEQ, the functional unit, and the memory unit. So you're going to have, 3 sets of 3, so you'll have 9 entries in total. 3 reservation stations, each reservation station was 3 entries. No up and halt instructions don't need a reservation entry because there's nothing to execute. But the question here is, when do you actually halt with the simulation?
That was a good question. We need a diagram.
We need a diagram.
Once the halt reaches the very end.
Of the?
Would need the diagram.
Reorder buffer. Once it reaches the head of the reorder buffer.
I should have guessed that one.
Yeah, come on, man. The reorder buffer's got your back, all right? It's all about the reorder buffer. If the reservation station or reorder buffer, either one, is full, stall all instructions in fetch, rename, and allocate until something is available. All right? Reservation station entries include source 1, the physical identifier, indexing to 16 ROB. Source 2, same thing. Destination, same thing. The value, once it's been forwarded, valid bit, whether it's correct or not. The value of source 2, valid bit. The operation to perform, aka load, store, add, NAND, branch if equal. Anything else that you may deem required, but this should be a good starting point for your simulation. This is for your reservation station. Your reorder buffer has a destination register, ID, the value, the valid bit, and any other storage requirement for correct function. I'll leave the instruction. Schedule. At most, 1 instruction can be executed by each functional unit each cycle. Instructions in the reservation station will with all source values available can be scheduled for execution. Multiple instructions are available. The instruction in the earliest program order use the destination physical register specifier and head pointer in the ROB to determine age. It's scheduled first, except that BEQs always have priority over adds and NANDs to reduce average branch penalty. Notice that you're shifting the BEQs to execute earlier. Once an instruction is scheduled, the reservation station entry is freed. It can be reallocated in the same cycle. It is freed. All right, here we go. Add NANDs and branch if equals take 1 cycle. Multiplies our pipeline and take 6 cycles to execute. A new multiply with all dependencies resolved can start executing 2 cycles after a previous multiply. If you remember from architecture, you can pipeline your multiplier such that you could have multiple pipelines working, or 2 of them working at the same time due to the way the hardware works. So while it takes 6 cycles, once it's 4 cycles in, if there's another multiply coming up, it can start as well. But multiply isn't completely pipelined as well. Loads and stores take 3 cycles and are not pipelined. We're just going to try and make that easier. To make it easier, stores can update memory contents at the end of execute, unlike the Premiere Pro, which is a little more difficult, but this should help simplify things. Once execution is complete, results are sent to the ROB, which is also the index in the ROB, and broadcast to all the reservation stations in case something needs to be updated. Once execution is complete, the reservation station entry for that instruction is freed. Great. Commit. Each cycle, the 2 oldest entries in the reorder buffer can be retired if they've completed execution. If only the oldest instruction is completed, then it's retired. If the oldest is not completed, no instructions can be retired. When retired, the ROB, reorder buffer, entry is freed, the register rename table is updated only if it still is mapped to the retired instruction, and the architecture register file is updated. Branch misprediction recovery occurs when the branch instruction is retired. Keep that in mind. Has to be retired before you can fix it. Reservation station and register rename tables must be clear. All right. Your task is to write a cycle. Let me make sure, Bart, you have more questions? No? All right, good. Your task is to write a cycle-accurate simulator for a little computer. At the start of the program, initialize the PC and all registers to 0. Run will be a loop where each iteration through the loop executes 1 cycle. At the beginning of the cycle, print the complete state of the machine and the body of the loop. You'll figure out what the new state of the machine, memory registers, pipeline register will be at the end of the cycle. Your simulation will halt when the halt instruction retires. Each cycle should print out which instructions are in the ROB from newest to oldest. At the end of the execute, you should print the cycles, cycle time to complete the program, fetched, number of instructions fetched, including instructions squashed because of branch misprediction. Make sure that's included.
It's with you.
Retired, how many were committed, how many branches were executed, how many branches were mispredicted. Your simulator should be run using a similar command. We already have the similar for last time, so it's the same thing.
Oh, I better implement that part.
Test cases, an integral and graded part of writing test cases, this is the same as the last time, will be to write a suite of test cases to validate any LC pipeline simulator. This is common practice in real-world software companies maintain a suite of test cases for their programs and use the suite to check the program's correctness after a change. All right, the test cases I'm going to grade just as much as last time, but write-up is very important. If you don't submit a write-up, your grade's going to be a 0. You will produce a document describing the overall operation of your simulator, as well as a discussion of how each test case demonstrates correct operation. Make sure you explain to me why you have certain test cases, and that'll give me confidence that things are working. This includes each instruction type, correctly forwarding all data hazards. There are many more data hazards now, so you need to...
Were these stipulations in the last project?
Not all of them, because you didn't have, you only had 1 data hazard in the last one. So look at this one for the previous one to make sure you're covering it. And correct operation of both the BTB and the branch predictor. The project write-up does not specify every aspect of the pipeline organization. Your write-up should explicitly state any design choices made, including a discussion of why you designed it and how it will be tested. In other words, I have not told you everything, and that is done intentionally because I want you to think about how you would design this processor if you were doing it. Make sure when you make a decision, you just write it down and tell me what it is you did, and then you'll get a good grade.
You're about to say, hey.
I was about ready to say it. Turning in your project, again, turn in via GitHub. That's hidden behind good old Google Hangouts, who's sharing everything now. Oh wait, I can click hide. All right, any questions, Matt? Nope, you got this. All right. Pause the recording.